Space fires invisible bullets of energy at Earth every single day. Each blast releases more power than our sun produces in a year. The bullets last just milliseconds. You think deep space stays quiet most of the time. That assumption is spectacularly wrong. Tonight we're tracking the most mysterious signals ever detected by radio telescopes. We'll discover why scientists had to invent an entirely new word for cosmic violence. Before we dive into these cosmic mysteries, drop a comment about what you think creates the strongest radio signals in space. If you enjoy these late-night space investigations, consider subscribing. These explorations of extreme physics are meant to be shared. Radio telescopes are like giant ears that listen to space. They pick up whispers from distant galaxies, gentle hums from gas clouds, steady beeps from spinning stars. They never expected to hear cosmic screams. In 2007, a scientist named Duncan Lorimer made an incredible discovery. He was digging through old telescope recordings looking for spinning stars called pulsars. Instead, he found something that shouldn't exist. A signal that lasted just 5 milliseconds. That's faster than you can blink. But in that tiny flash, it blazed brighter than entire galaxies filled with billions of stars. This wasn't a broken telescope. The signal had traveled billions of light years through empty space to reach us. Scientists could tell because different colors of radio waves arrived at slightly different times. This only happens when signals cross the vast emptiness between galaxies. They called it the Lorimer burst. They had no idea they'd discovered the first fast radio burst, a completely new type of cosmic explosion. These cosmic lightning bolts pack impossible amounts of energy into time frames shorter than a camera flash. 3 milliseconds. Less time than it takes to blink your eyes. Yet in that instant, they release more energy than our sun produces in 12 months. The incredible briefness tells us something shocking about whatever creates them. The source must be smaller than Earth, but more violent than anything we can imagine. Only the most extreme objects in the universe can squeeze such enormous power into such tiny moments. One burst releases about a billion joules of energy. That equals all the electricity used by every human on Earth for thousands of years, all concentrated into the time between heartbeats. These signals travel across most of the visible universe and still arrive strong enough for our telescopes to detect. Whatever fires them briefly outshines the combined radio glow of hundreds of billions of stars. Every fast radio burst carries a hidden signature of its incredible journey. High-pitched radio notes arrive first. Low-pitched notes arrive slightly later. This creates what scientists call a frequency chirp. This timing pattern doesn't happen by accident. It reveals that these signals have crossed unimaginable distances through space filled with scattered particles. As radio waves travel through the universe, they bump into free electrons floating between galaxies. Higher frequencies move slightly faster than lower frequencies through this cosmic obstacle course. The longer the journey, the bigger the time difference. Scientists use this timing difference to measure distance. The bigger the chirp, the farther the signal has traveled. Most fast radio bursts show chirp patterns indicating they've crossed billions of light years. They're messages from the edge of the observable universe. The chirp pattern in fast radio bursts does more than measure distance. It reveals invisible matter hiding throughout the universe that we never knew existed. For decades, astronomers had a mystery. They could count all the stars and galaxies they could see. But according to the laws of physics, the universe should contain much more ordinary matter. About half of it was simply missing. Fast radio bursts solve this cosmic mystery. As their signals travel across billions of light years, they interact with electrons scattered throughout supposedly empty space. These interactions create the timing delays we observe. Scientists can now map this invisible matter using fast radio burst signals as cosmic flashlights. The missing matter isn't actually missing. It's spread throughout the vast spaces between galaxies as hot, thin gas too faint for our telescopes to see directly. Fast radio bursts revealed the universe's hidden skeleton. Most fast radio bursts happen once and never repeat. Scientists detect the flash, record the data, then never hear from that location again. These one-time events seem to destroy whatever creates them. But some sources break this rule completely. They fire multiple bursts from the same spot in space. The first repeating source, called FRB 121102, has produced hundreds of individual bursts over several years. Repeating sources behave completely differently from one-time events. They're typically less powerful per burst, but more active overall. They come from younger, star-forming galaxies. One-time bursts usually come from older, quieter galaxies. This suggests two entirely different types of cosmic catastrophes create fast radio bursts. One destroys its source in a single violent explosion. The other allows repeated outbursts from the same extreme object. Scientists discovered the first major clue about what creates fast radio bursts in our own galaxy. In April 2020, a highly magnetic dead star called a magnetar produced a fast radio burst. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. These crushed stellar cores pack the mass of our Sun into a sphere smaller than a city. Their magnetic fields are so intense they would erase every credit card on Earth from the distance of the Moon. The magnetar SGR 1935 plus 2154 suddenly erupted with a burst of radio energy. It was much weaker than typical fast radio bursts from other galaxies, but it showed the same basic characteristics. For the first time, scientists could directly observe a fast radio burst source. This discovery suggests that supermagnetic neutron stars create at least some fast radio bursts. Sudden cracks in their incredibly strong magnetic fields release enormous amounts of energy in milliseconds. But this probably doesn't explain all fast radio bursts, especially the most powerful ones. The most powerful one-time fast radio bursts might come from cosmic collisions so violent they destroy both objects involved. When two neutron stars spiral together and merge, they release more energy in seconds than our Sun will produce in its entire lifetime. These collisions create gravitational waves that ripple through space-time itself. They also produce gamma-ray bursts visible across the universe. Scientists now suspect they might also fire fast radio bursts during the final moments before impact. The merger completely destroys both neutron stars, creating either a black hole or a single, more massive neutron star. This would explain why the most powerful fast radio bursts never repeat. Their sources literally no longer exist. Other violent events might also create one-time fast radio bursts. A neutron star falling into a black hole would produce an incredible burst of energy just before disappearing forever. Even the collapse of certain types of stars could fire a fast radio burst as a final death scream. For the first 10 years after discovery, scientists could only find fast radio bursts by analyzing old telescope data. By the time they detected a burst, it was already over and the telescope had moved on to observe something else. Everything changed when telescopes learned to detect fast radio bursts in real time. The moment a burst arrives, Automated systems instantly alert other telescopes around the world. This allows immediate follow-up observations while the source might still be active. The Canadian Hydrogen Intensity Mapping Experiment, called CHIME, revolutionized fast radio burst discovery. This unique telescope design can monitor huge portions of the sky continuously. It detects dozens of new fast radio bursts every month. Real-time detection allows scientists to study the aftermath of fast radio bursts. They can search for optical flashes, X-ray emission, or other signals that might accompany the radio burst. This multi-wavelength approach is revealing the full picture of these cosmic explosions. Radio telescopes receive millions of signals every day. Most come from human technology: cell phones, satellites, microwave ovens, car engines. Finding real cosmic signals in this electronic noise was nearly impossible until artificial intelligence joined the hunt. Machine learning systems now analyze telescope data in real time. They're trained to recognize the specific patterns that distinguish genuine fast radio bursts from terrestrial interference. The AI can process data faster than any human and never gets tired. These smart systems look for multiple characteristics simultaneously: the frequency chirp pattern indicating cosmic distance, the specific duration and brightness profile, the polarization of the radio waves. Only signals matching all criteria get flagged as potential fast radio bursts. Human astronomers still verify every candidate before confirming a discovery. But machine learning has increased the detection rate by orders of magnitude. We now discover more fast radio bursts in a single month than were found in the first decade after the original Lorimer burst. The next generation of radio telescopes will transform fast radio burst science. The Square Kilometer Array will become the most sensitive radio telescope ever built, spread across 2 continents with collecting area equivalent to a square kilometer. This unprecedented sensitivity will detect thousands of fast radio bursts every single day. Scientists will be able to study even the weakest bursts from the most distant galaxies. They'll map fast radio burst sources across cosmic time, tracing the history of extreme events throughout the universe. Advanced telescope arrays will pinpoint fast radio burst locations with incredible precision. They'll identify the exact galaxies and even specific regions within galaxies where bursts originate. This will reveal what types of environments produce these extreme explosions. Combining fast radio burst observations with gravitational wave detectors and space-based telescopes will provide complete pictures of cosmic catastrophes. Scientists expect to solve the mystery of what creates fast radio bursts within the next decade. Fast radio bursts have evolved from mysterious anomalies into powerful tools for studying the universe itself. Their signals probe the structure of space between galaxies, revealing matter too faint for any other detection method. Scientists use fast radio bursts as cosmic rulers to measure distances across the universe. The amount of matter a signal encounters during its journey indicates how far it has traveled. This provides a new way to study the expansion of the universe itself. The polarization of fast radio burst signals maps magnetic fields throughout cosmic space. As the radio waves travel through magnetized plasma, their polarization twists in measurable ways. This reveals the hidden magnetic skeleton of the universe. Fast radio bursts might even help detect dark matter, the mysterious substance that makes up most of the universe's mass. Any interaction between dark matter and fast radio burst signals could reveal the true nature of this cosmic ghost. These brief cosmic screams have become windows into the deepest secrets of space and time. Could the most important discovery in radio astronomy have been sitting unnoticed in old data for years? That's exactly what happened with the first fast radio burst. In 2007, Duncan Lorimer wasn't looking for anything new. He was a pulsar researcher at West Virginia University digging through archived observations from the Arecibo telescope. Pulsars are rapidly spinning neutron stars that flash radio beams like cosmic lighthouses. Scientists had been studying them for decades. Lorimer was searching through 6-year-old data recordings from a pulsar survey. The computer analysis was routine work, looking for the regular rhythmic pulses that identify these spinning stellar remnants. Instead, something completely unexpected appeared on his screen. A single, incredibly bright flash that lasted just 5 milliseconds. It didn't repeat. It didn't match any known pulsar signature. The burst was so powerful it overwhelmed the telescope's receivers. Yet it came from a completely empty patch of sky billions of light years away. The signal that would change radio astronomy forever almost went unnoticed. Duncan Lorimer and his student David Narkevic spent months verifying their discovery before daring to publish it. They had to be absolutely certain this wasn't a mistake. The Lorimer burst, as it came to be known, appeared in observations from July 24, 2001. But the discovery didn't happen until 2007, when improved data processing techniques revealed the hidden signal. This 6-year delay showed how easy it was to miss these brief cosmic flashes. When Lorimer's team finally published their findings, they described something that shouldn't exist according to known physics. A radio source that briefly outshone entire galaxies, lasted less time than a camera flash, and then vanished completely. No known cosmic object could produce such extreme behavior. The scientific paper that announced this discovery created a completely new category of astronomical phenomena. Within months, other researchers around the world began searching their own archived data for similar signals. The hunt for fast radio bursts had officially begun. Radio telescopes face a constant battle against human-made interference. Cell phone towers, satellites, microwave ovens, and even passing cars create radio signals that can contaminate astronomical observations. When the first fast radio bursts appeared, many scientists naturally assumed they were looking at terrestrial pollution. The Lorimer burst showed several suspicious characteristics that suggested earthly origins. It appeared just once, making it impossible to verify through repeated observations. Its incredible brightness seemed too extreme for any known cosmic source. Most troubling, it came from a direction in space where no significant radio sources had been detected before. Several research teams initially dismissed fast radio burst candidates as radio frequency interference, or RFI. They developed sophisticated algorithms to filter out signals that seemed too brief, too bright, or too isolated to be genuine astronomical phenomena. This skepticism was scientifically appropriate but temporarily slowed the pace of discovery. The controversy persisted until researchers found ways to distinguish genuine cosmic signals from terrestrial interference. True fast radio bursts showed specific characteristics that human technology rarely produces, including the frequency-dependent time delays that indicate propagation across cosmic distances. Archive diving could only take fast radio burst research so far. Looking through old telescope data was like trying to study lightning by examining photographs taken randomly during storms. Scientists needed to catch these cosmic flashes in the act. Real-time detection presented enormous technical challenges. Fast radio bursts last just milliseconds and arrive without warning from random directions. Telescopes had to process incoming data instantly, recognize potential bursts within seconds, and alert other observatories before the signal information became stale. The first breakthrough came when researchers developed automated detection pipelines that could analyze telescope data as it arrived. These systems use powerful computers to search for the characteristic signatures of fast radio bursts in real time, flagging candidates within minutes of detection. Real-time detection revolutionized fast radio burst research by enabling immediate follow-up observations. When one telescope detected a burst, it could instantly alert optical telescopes, X-ray satellites, and other radio dishes to search for additional signals from the same location. This coordination was impossible when working with archived data discovered years after the original observation. Australia's Parkes Radio Telescope became the champion of fast radio burst detection. This 64-meter dish in New South Wales found burst after burst, confirming that the Lorimer discovery wasn't a one-time fluke. The telescope's location in the southern hemisphere gave it access to parts of the sky rarely monitored by northern observatories. Between 2008 and 2014, the Parkes telescope detected more than a dozen additional fast radio bursts. Each discovery strengthened the case that these signals represented a genuine new class of cosmic phenomena rather than equipment malfunctions or interference. The bursts came from different directions, showed varying strengths, and displayed the same characteristic frequency sweeps. The Parkes discoveries revealed important patterns about fast radio burst behavior. Most lasted between 1 and 10 milliseconds. All showed the downward frequency drift that indicated propagation through intergalactic space. None repeated from the same location, suggesting they came from catastrophic one-time events. These confirmations from an independent telescope using different equipment eliminated most remaining doubts about fast radio burst authenticity. The Parkes observations proved that brief, powerful radio flashes from distant cosmic sources were a real and repeatable phenomenon deserving serious scientific study. New scientific phenomena need names, and fast radio bursts initially went by several different labels. Early papers referred to them as brief intense radio flashes, millisecond radio bursts, or simply anomalous pulses. The terminology was inconsistent and confusing for researchers trying to build on each other's work. The term fast radio burst was proposed in 2013 by researchers who wanted a clear, descriptive name that captured the phenomenon's key characteristics. The acronym FRB quickly became standard throughout the astronomical community. This naming consistency was crucial for organizing research and developing databases. Along with standardized terminology came systematic naming conventions. Each confirmed fast radio burst receives a unique identifier starting with FRB, followed by the date of discovery. For example, FRB 121102 was discovered on November 2, 2012. This numbering system allows researchers worldwide to reference specific events without confusion. The establishment of standard terminology and numbering systems marked fast radio burst research transition from informal curiosity to formal scientific discipline. These conventions enabled systematic study, database construction, and collaborative research that would have been impossible with inconsistent naming schemes. Fast radio bursts democratized radio astronomy in unexpected ways. Unlike phenomena that require the world's largest telescopes, fast radio bursts could be detected by relatively modest radio dishes with the right equipment and processing power. This accessibility sparked a global collaboration involving dozens of observatories. The initial discoveries by American and Australian telescopes quickly inspired similar searches at radio facilities across Europe, Asia, and Africa. Each telescope brought unique capabilities. Some excelled at wide-field surveys, Others provided precise timing, and still others offered extreme sensitivity to weak signals. International coordination became essential when real-time detection enabled immediate follow-up observations. A fast radio burst detected in Australia could trigger observations at telescopes in Chile, Spain, and South Africa within minutes. This global network multiplied the scientific value of each detection. The collaboration extended beyond radio astronomy to include optical telescopes, X-ray satellites, and gravitational wave detectors. Multi-wavelength observations became possible when different types of telescopes could respond to fast radio burst alerts within seconds of the initial detection. Individual fast radio burst discoveries were valuable, but patterns only emerged when researchers could analyze large numbers of events together. This required systematic databases that could store, organize, and compare observations from telescopes around the world using different equipment and analysis techniques. The first comprehensive fast radio burst catalog was created by researchers at the University of Manchester. They collected published observations, extracted key parameters like position, brightness, and duration, and standardized the data formats for easy comparison. This database became the foundation for population studies. Database construction revealed the first statistical patterns in fast radio burst properties. Researchers could determine typical durations, brightness distributions, and arrival rate patterns. They found that fast radio bursts occurred roughly once every few seconds somewhere in the observable universe, making them among the most common high-energy phenomena in space. Modern fast radio burst databases contain thousands of events and continue growing rapidly as detection rates increase. These archives enable machine learning approaches to classification, help identify unusual events that warrant special attention, and provide the statistical foundation for theoretical modeling of fast radio burst sources. Radio telescopes detect millions of signals every day. Most come from human technology, equipment malfunctions, or atmospheric effects rather than cosmic sources. Developing reliable methods to separate genuine fast radio bursts from false alarms became crucial as the field grew and detection rates increased. False positives could arise from many sources. Lightning creates brief radio flashes. Satellite transmissions can mimic cosmic signals. Even microwave ovens in nearby buildings can trigger detection algorithms when they cycle on and off. Each false alarm wastes valuable follow-up resources and corrupts statistical analysis. Researchers developed multi-stage verification procedures to minimize false positives. Candidate signals must pass tests for cosmic origin, including the characteristic frequency-dependent delays that indicate propagation through intergalactic space. They must appear in multiple telescope beams simultaneously and show polarization patterns consistent with cosmic radio sources. The most stringent verification requires independent confirmation by multiple telescopes. A signal detected by only one instrument remains a candidate until verified by others. This conservative approach sacrifices some detection efficiency but ensures that published fast radio burst catalogs contain only genuine cosmic phenomena. Fast radio burst research transformed from a curiosity pursued by a few specialists into one of astronomy's hottest fields. The number of scientific papers about fast radio bursts doubled every 2 years after 2010, reflecting the phenomenon's growing importance and the expanding community of researchers. The appeal came from fast radio bursts' unique combination of extreme physics and accessibility. These events probe conditions more extreme than anything achievable on Earth, yet they can be studied with relatively modest equipment. graduate students could make important discoveries using data from small university telescopes. Research directions multiplied rapidly as different groups explored various aspects of fast radio burst science. Theorists proposed dozens of source models. Observers developed new detection techniques. Engineers built specialized instruments optimized for fast radio burst searches. The field's breadth attracted talent from across astronomy and physics. By 2020, fast radio burst research had evolved into a mature scientific discipline with dedicated conferences, specialized journals, and international coordination committees. What began as an accidental discovery in archived data had grown into one of the most active and productive areas of modern astrophysics. What happens when cosmic objects briefly outshine entire galaxies? Fast radio bursts achieve peak brightnesses that dwarf every other radio source in the known universe. Peak luminosity measures how much energy an object radiates per second at its brightest moment. Our Sun produces about 4 billion watts of power continuously. That seems enormous until you compare it to a fast radio burst. During their brief flash, the most powerful fast radio bursts reach peak luminosities 1 trillion times greater than our Sun. They become temporarily brighter than all 400 billion stars in the Milky Way combined. This incredible brightness lasts just milliseconds before vanishing completely. No steady radio source in the universe approaches these peak values. Even supermassive black holes actively feeding on surrounding matter produce only a tiny fraction of this radio power. Fast radio bursts represent the absolute extreme of cosmic radio emission. Scientists measure something called brightness temperature to understand how radio sources work. This isn't the actual physical temperature of the object. Instead, it's a calculation that reveals how efficiently the source produces radio waves. Most cosmic radio sources have brightness temperatures of a few thousand degrees. Our Sun's radio emissions correspond to brightness temperatures around 10,000 degrees. Hot gas clouds might reach 1,000,000 degrees. These are already considered quite hot by astronomical standards. Fast radio bursts shatter these scales completely. Their brightness temperatures exceed 100 billion degrees. That's billions of times hotter than the core of the Sun, where nuclear fusion occurs at 15 million degrees. Such extreme brightness temperatures indicate that fast radio bursts cannot be produced by normal thermal processes. The radio waves must be generated by highly organized, coherent emission mechanisms that we don't fully understand. Fast radio bursts aren't just brief overall. They contain internal structure on timescales almost too short to measure. Advanced radio telescopes can detect variations in brightness that last just microseconds. A microsecond is 1/1,000,000th of a second. Light travels only 300 meters in that time. The entire burst might last 5 milliseconds, but within that brief flash, scientists detect fluctuations that rise and fall in microseconds. This fine-scale structure tells us something profound about the emission mechanism. Whatever creates fast radio bursts must be operating on spatial scales smaller than a few hundred meters. That's incredibly compact for something producing such enormous energy. The microsecond variability also rules out many potential source models. Large objects like normal stars cannot change their brightness on such short timescales because light takes time to travel across their surfaces. Random radio emission from hot gas creates a gentle background hum. Fast radio bursts produce something completely different. Their radio waves are coherent, meaning they're perfectly synchronized like laser light. Coherent emission occurs when countless particles move in perfect harmony. creating radio waves that add together constructively. Instead of random static, you get an organized, powerful beam. This is similar to how a laser produces intense light by synchronizing photons. The coherent nature of fast radio burst emission explains their incredible brightness. Random thermal emission could never reach such extreme intensities. Only highly organized processes can produce the synchronized radio waves we observe. This discovery revolutionized thinking about fast radio burst sources. Scientists now know they're looking for mechanisms that can organize vast numbers of particles into coherent motion within milliseconds. Very few cosmic processes can achieve such precise coordination. Most cosmic radio sources are picky about frequency. They might shine brightly at one radio wavelength but remain dim at others. Fast radio bursts broadcast simultaneously across enormous ranges of radio frequencies. Bandwidth measures the range of frequencies an object emits. AM radio stations use narrow bandwidths of just a few kilohertz. Even the broadest cosmic radio sources rarely exceed a few megahertz. Fast radio bursts span several hundred megahertz simultaneously. This broad bandwidth emission requires special conditions. The source must be able to generate radio waves across a wide spectrum all at once. This suggests highly energetic processes involving particles moving at significant fractions of the speed of light. The simultaneous multi-frequency emission also helps distinguish genuine fast radio bursts from terrestrial interference. Human technology rarely produces such broadband signals with the specific characteristics observed in cosmic fast radio bursts. Radio waves can vibrate in different directions as they travel through space. This property is called polarization, and it reveals important information about the magnetic fields where the radio waves originated. Most cosmic radio sources produce unpolarized emission, with radio waves vibrating randomly in all directions. This happens when magnetic fields are tangled and chaotic. Strong, organized magnetic fields create polarized radio waves that vibrate in preferred directions. Fast radio bursts often show high degrees of linear polarization. The radio waves vibrate predominantly in one direction rather than randomly. This indicates the presence of strong, well-organized magnetic fields at the emission site. Some fast radio bursts show polarization levels exceeding 50%. This means more than half the radio waves are aligned in the same direction. Such high polarization requires magnetic field strengths and organization that exist only in the most extreme cosmic environments. Fast radio bursts don't end abruptly. They fade away gradually in a characteristic pattern called an exponential scattering tail. This tail reveals details about the matter the radio waves encountered during their cosmic journey. Scattering occurs when radio waves interact with free electrons in space. The waves get slightly deflected, causing some to arrive later than others. Higher frequencies scatter less than lower frequencies, creating the distinctive tail pattern. The length and shape of the scattering tail depends on how much turbulent matter the signal passed through. Longer tails indicate more interactions with cosmic plasma. Some fast radio bursts show minimal scattering, while others display prominent tails lasting several milliseconds. Scattering analysis helps scientists map the distribution of matter between galaxies and within the host galaxy where each fast radio burst originated. This makes fast radio bursts valuable probes of cosmic structure. Fluence measures the total amount of energy a fast radio burst releases during its entire duration. Unlike peak luminosity, which captures the maximum power, fluence accounts for every bit of energy emitted from start to finish. Scientists calculate fluence by measuring the brightness of a fast radio burst and multiplying by its duration. Even though these events last just milliseconds, their extreme peak brightness results in enormous total energy output. Typical fast radio bursts release fluences equivalent to what our sun produces in several weeks or months. The most powerful events equal 6 months of total solar energy output, all compressed into a few milliseconds of radio emission. This energy calculation assumes the radio emission spreads equally in all directions. If fast radio bursts actually beam their energy in narrow cones, the total energy requirements could be even higher to produce the brightnesses we observe. Different emission mechanisms produce characteristic patterns in how brightness varies with frequency. This relationship is called the spectral index, and it provides crucial clues about the physics creating fast radio bursts. A spectral index measures whether a source is brighter at high frequencies or low frequencies. Thermal emission from hot gas typically produces one type of spectral index. Synchrotron emission from high-energy particles creates a different pattern. Most fast radio bursts show spectral indices consistent with non-thermal emission mechanisms. The radio waves don't come from simple heating of matter. Instead, they appear to originate from high-energy particles spiraling in strong magnetic fields. The specific spectral index values help scientists distinguish between competing theoretical models for fast radio burst sources. Different proposed mechanisms predict different spectral behaviors that can be tested against observations. Radio astronomy requires detecting incredibly weak signals against noisy backgrounds. Fast radio bursts present the opposite challenge. They're so bright they can overwhelm telescope receivers designed for normal cosmic whispers. Dynamic range measures the difference between the strongest and weakest signals a system can handle simultaneously. Most radio telescopes are optimized for detecting faint sources, with dynamic ranges of perhaps 1,000,000 to 1. Fast radio bursts exceed these limits by factors of 10 or more. The peak signal can be 10 million times brighter than the background noise level. This extreme dynamic range challenges the electronics in radio telescope systems. Some fast radio bursts are so bright they saturate telescope receivers, making it impossible to measure their true peak brightness. Scientists must use indirect methods to estimate the actual signal strength of the most powerful events. When fast radio bursts are too bright, they break the very instruments trying to measure them. Radio telescope receivers have maximum signal levels they can handle before becoming saturated and producing incorrect readings. Saturation occurs when the incoming signal exceeds the electronic limits of the detection system. Instead of measuring the true brightness, the receiver outputs its maximum possible value regardless of how much brighter the actual signal might be. Many of the most powerful fast radio bursts show clear signs of receiver saturation. The measured brightness reaches the telescope's maximum limit and stays there throughout the burst duration. This creates a flat top signal profile instead of the true burst shape. Scientists must carefully design new receivers with higher dynamic ranges to accurately measure the brightest fast radio bursts. Understanding the true energy scales requires instrumentation that won't be overwhelmed by these cosmic extremes. Individual fast radio bursts often contain complex internal structure. What appears to be a single flash actually consists of multiple smaller bursts occurring in rapid succession. These subcomponents reveal additional complexity in the emission mechanism. High-resolution analysis shows that many fast radio bursts contain 2 to 5 distinct subbursts separated by microseconds or milliseconds. Each subcomponent has its own brightness profile and duration. Together, they create the overall fast radio burst envelope. The subburst structure varies dramatically between different fast radio bursts. Some show regularly spaced components suggesting periodic processes. Others display chaotic patterns with irregular spacing and varying amplitudes. This internal complexity indicates that fast radio burst sources don't produce single, smooth energy releases. Instead, they appear to undergo multiple rapid-fire emission episodes within the overall event duration, suggesting highly dynamic and unstable physical conditions at the source. Radio waves of different colors don't all travel at exactly the same speed through space. This seemingly small effect becomes the key to measuring distances across the universe. When a fast radio burst travels through space, it encounters scattered electrons floating in the vast emptiness between galaxies. These electrons interact more strongly with low-frequency radio waves than high-frequency ones. The result is a measurable delay. High-pitched radio signals arrive at Earth first. Low-pitched signals from the same burst arrive slightly later. The time difference between frequencies reveals exactly how many electrons the signal encountered during its cosmic journey. Scientists call this measurement the dispersion measure, or DM. It's calculated by measuring the precise arrival time of different radio frequencies and converting the delays into electron density units. The more electrons encountered, the larger the dispersion measure becomes. Before fast radio bursts, astronomers needed a way to map electron density throughout our own galaxy. They developed this map using thousands of pulsars as cosmic lighthouses with known distances. The N.E.-Mackenzie model represents decades of careful measurement and modeling. Scientists observed pulsars at known distances, measured their dispersion delays, and calculated how many electrons must exist in each direction through the Milky Way. This model divides our galaxy into a three-dimensional grid. Each grid cell contains an estimate of electron density based on pulsar observations. The model accounts for the galaxy's disk structure, spiral arms, and central bulge regions. Without this galactic electron map, scientists cannot determine how much of a fast radio burst dispersion comes from our own galaxy versus the vast distances beyond. The model provides the crucial baseline for cosmic distance measurements. Fast radio burst signals accumulate dispersion delays from three distinct regions during their cosmic journey. Separating these contributions requires careful subtraction of known galactic effects. The total measured dispersion includes delays from our own Milky Way galaxy, the vast space between galaxies, and the host galaxy where the fast radio burst originated. Only the intergalactic component directly indicates cosmological distance. Scientists subtract the predicted galactic contribution using the N.E.-Mackenzie model. The remaining excess dispersion measure represents electrons encountered in intergalactic space, plus any contribution from the host galaxy environment. This excess dispersion becomes the primary tool for estimating fast radio burst distances. The larger the excess, the farther the signal has traveled through intergalactic space to reach us. Dispersion measures from fast radio bursts provide a completely independent way to study the expanding universe. This method doesn't rely on traditional distance indicators like supernovae or galaxy brightness measurements. As the universe expands, space itself stretches the wavelengths of light and radio waves traveling through it. This stretching, called redshift, increases with distance. The amount of matter encountered also increases with distance as signals traverse more cosmic volume. The relationship between dispersion measure and redshift depends on the universe's expansion history and matter content. Different cosmological models predict slightly different relationships that can be tested against fast radio burst observations. Thousands of fast radio burst distance measurements could revolutionize cosmology by providing precise constraints on dark energy, the mysterious force driving cosmic acceleration. For decades, cosmologists faced an embarrassing problem. They could calculate how much ordinary matter should exist in the universe, but they could only find about half of it in stars and galaxies. This missing ordinary matter, called baryons, wasn't exotic dark matter. It consisted of normal protons and neutrons that should be detectable but somehow remained hidden from telescopes. Fast radio bursts solved this cosmic accounting problem. Their dispersion measurements revealed vast quantities of ionized gas spread throughout intergalactic space. This hot, thin plasma was too faint for direct observation, but dense enough to affect radio wave propagation. The electron densities inferred from fast radio burst observations perfectly account for the missing baryons. Half the universe's ordinary matter exists as hot intergalactic gas filling the spaces between galaxy clusters. Temperature affects how electrons interact with radio waves. The intergalactic medium isn't uniformly cold. It contains regions heated by various cosmic processes that can slightly alter dispersion measurements. Hot intergalactic gas produces slightly different dispersion effects than cold gas at the same density. These temperature corrections are typically small but become important for precision distance measurements to the most distant fast radio bursts. Scientists must estimate intergalactic medium temperatures using theoretical models and observations of galaxy clusters. Typical temperatures range from 10,000 to several million degrees depending on location and cosmic environment. Ignoring temperature effects introduces systematic errors in distance estimates. Proper correction requires detailed modeling of intergalactic medium physics and careful calibration against other distance measurement techniques. Every fast radio burst originates within a host galaxy containing its own population of electrons. Separating this local contribution from the cosmological dispersion signal presents major challenges for distance estimation. Host galaxies vary dramatically in size, star formation rate, and internal structure. A burst from a massive, active galaxy will encounter many more internal electrons than one from a small, quiet galaxy. The host galaxy contribution cannot be directly measured. It must be estimated using statistical models based on galaxy properties inferred from optical observations. These estimates carry large uncertainties. Host galaxy dispersion uncertainty limits the precision of cosmological distance measurements. Future observations must better characterize host galaxy properties to improve fast radio burst cosmology applications. Dispersion measures the average electron density along a fast radio burst's path. Scattering measure reveals how clumpy and turbulent that electron distribution actually is. Scattering occurs when radio waves encounter small-scale variations in electron density. These fluctuations deflect radio waves slightly, causing some to arrive later than others and creating the exponential tails observed in many fast radio burst profiles. The amount of scattering depends on both the total electron content and the degree of turbulence in the plasma. Smooth electron distributions produce little scattering. Highly turbulent regions create prominent scattering tails. Scattering measurements provide information about intergalactic medium physics that cannot be obtained from dispersion alone. They reveal the three-dimensional structure of cosmic plasma on scales from kilometers to light years. Fast radio bursts don't occur in empty space. They explode within dense stellar environments that can significantly contaminate dispersion measurements with local electron contributions. The immediate vicinity of a fast radio burst source might contain supernova remnants, stellar winds, or ionized gas clouds. These local environments can have electron densities millions of times higher than typical intergalactic space. Even small amounts of high-density material along the line of sight can dominate the total dispersion measure. This local contamination makes it difficult to extract the cosmological component needed for distance estimation. Accounting for environmental contributions requires detailed modeling of fast radio burst source environments. Different source models predict different local electron densities that can be tested against observations. Fast radio bursts offer a completely new tool for measuring cosmic distances. Unlike traditional methods that depend on stellar brightness or galaxy properties, dispersion measures directly probe the matter between source and observer. The relationship between dispersion measure and distance depends only on fundamental physics and cosmology. It doesn't suffer from the systematic uncertainties that plague other distance indicators like dust extinction or stellar evolution. Developing this distance scale requires careful calibration against fast radio bursts with independent distance measurements. Repeating sources with optical counterparts provide the best calibration opportunities. Once calibrated, fast radio burst distance measurements could extend cosmic distance scales to higher redshifts and provide independent checks on universe expansion measurements from other techniques. Every fast radio burst distance measurement carries uncertainties from multiple sources. Understanding and minimizing these errors is crucial for cosmological applications. Model uncertainties arise from incomplete knowledge of electron density distributions in galaxies, intergalactic space, and source environments. Different models can predict significantly different distance estimates for the same fast radio burst. Observational errors include measurement uncertainties in dispersion timing, telescope calibration problems, and interference from Earth-based radio sources. Each error source must be carefully characterized and minimized. Statistical analysis of large fast radio burst samples can identify and correct for systematic biases. As detection rates increase, statistical methods become increasingly powerful for isolating cosmological signals from measurement noise. One fast radio burst changed everything scientists thought they knew about these cosmic explosions. FRB 121102 broke the fundamental rule that fast radio bursts happen once and disappear forever. This source was first detected in November 2012 by the Arecibo telescope in Puerto Rico. Initially, it seemed like just another one-time event. Scientists recorded the burst, cataloged its properties, and moved on to other observations. Then something unprecedented happened. The same location in space produced another fast radio burst. Then another, and another. Over several years, FRB 121102 has generated hundreds of individual bursts from the exact same point in the sky. This discovery revolutionized fast radio burst science by proving that at least some sources can fire multiple times. Whatever creates FRB 121102 survives its own explosions and remains capable of producing additional bursts over extended periods. Repeating fast radio bursts don't fire randomly. They follow mysterious activity cycles that alternate between busy periods of frequent bursts and quiet phases with no detectable emission. FRB 121102 shows clear evidence of cyclical behavior. For weeks or months, it produces bursts almost daily. Then it suddenly goes quiet for extended periods, sometimes remaining silent for over a year before resuming activity. During active phases, the source can produce multiple bursts per day with highly variable brightness and timing. Some bursts occur within minutes of each other, while others are separated by hours or days. The pattern appears chaotic within the active periods. These activity cycles suggest that repeating fast radio burst sources undergo periodic changes in their physical conditions. Something in the source environment triggers episodes of enhanced burst production followed by dormant recovery phases. Two types of galaxies host two types of fast radio bursts. This environmental difference provides crucial clues about what creates these mysterious signals. Repeating fast radio bursts like FRB 121102 consistently appear in young, actively star-forming galaxies. These galaxies contain hot blue stars, active stellar nurseries, and ongoing supernova explosions. The environments are dynamic and energetic. One-time fast radio bursts show the opposite preference. They typically originate in older, more mature galaxies where star formation has largely ceased. These galaxies contain primarily older, redder stars and much less ongoing stellar activity. The correlation between burst behavior and galaxy type suggests that repeating and one-time fast radio bursts arise from fundamentally different stellar populations or evolutionary phases. Young stellar environments apparently favor repeating sources, while older populations produce single burst events. Pinpointing the exact location of a cosmic explosion that lasts just milliseconds presents enormous technical challenges. Repeating fast radio bursts provide the solution through multiple observation opportunities. Single burst events disappear before telescopes can coordinate precise position measurements. Scientists get one brief chance to detect the signal and must estimate its location from that single observation. Position uncertainties can span entire galaxy clusters. Repeating sources allow multiple position measurements that can be combined for extraordinary precision. Each new burst provides additional data to refine the location estimate. After dozens of detections, scientists can determine positions accurate to milliseconds of arcs. This precision makes it possible to identify the specific host galaxy and even pinpoint regions within that galaxy where the fast radio burst originates. Such detailed localization is essential for understanding source environments and testing theoretical models. Power output patterns reveal another fundamental difference between fast radio burst populations. The two types show distinctly different energy preferences that hint at their underlying physics. Repeating fast radio bursts typically produce individual bursts with relatively modest energies. Each burst releases energy equivalent to what our sun produces in a few days or weeks. These sources compensate for lower individual energies by firing many bursts over time. One-time fast radio bursts show the opposite pattern. They tend to produce single bursts with enormous energies equivalent to months or years of solar output. These events are much more powerful individually but occur just once. The energy distribution difference suggests that repeating sources operate under different physical constraints than one-time events. Repeating sources may be limited to lower individual energies, but can sustain burst production over extended periods. Radio wave polarization carries information about magnetic fields at the emission site. Repeating in one-time fast radio bursts show dramatically different polarization behaviors that reveal distinct source environments. Repeating fast radio bursts often display complex, time-variable polarization properties. The polarization angle can change significantly between different bursts from the same source. Some show evidence of extreme rotation measures indicating passage through highly magnetized environments. One-time fast radio bursts typically show simpler polarization patterns. Their polarization properties appear more stable and less extreme. The rotation measures suggest passage through more typical cosmic magnetic field environments. The complex polarization behavior of repeating sources indicates they exist in highly dynamic magnetic field environments. The changing polarization patterns suggest the magnetic field structure around these sources evolves over time scales of days to months. Frequency coverage provides another diagnostic tool for distinguishing between fast radio burst populations. The two types occupy different portions of the radio spectrum in characteristic ways. Repeating fast radio bursts typically emit across relatively narrow frequency ranges. They might cover a few hundred megahertz of bandwidth centered on specific frequencies. The emission often shows complex internal structure within this limited range. One-time fast radio bursts generally display broader bandwidth emission. They can simultaneously broadcast across several gigahertz of radio spectrum, covering much wider frequency ranges than their repeating counterparts. The narrower bandwidth of repeating sources suggests they operate through more frequency-selective emission mechanisms. This could indicate different magnetic field geometries or particle acceleration processes compared to the broadband emission of one-time events. Every burst from a repeating source looks different, yet patterns emerge when scientists analyze large numbers of events. This combination of diversity and consistency reveals important clues about emission mechanisms. Individual bursts from FRB 121102 show remarkable variety in their temporal structure. Some appear as single smooth pulses, others display multiple peaks, and some show complex irregular profiles. No two bursts look exactly alike. Despite this morphological diversity, statistical analysis reveals underlying consistencies. The distribution of burst durations, peak frequencies, and energy outputs remains relatively stable over time. The chaos appears random but follows predictable statistical rules. This behavior suggests that repeating fast radio burst sources operate through stochastic processes that can produce varied outcomes while maintaining consistent average properties. The source mechanism may involve random triggering of similar underlying physical processes. Growing evidence suggests that repeating and one-time fast radio bursts represent completely different classes of cosmic phenomena. They may arise from entirely separate types of astronomical objects. The systematic differences in energy, environment, polarization, and bandwidth indicate fundamental distinctions in source physics. These differences are too consistent to result from minor variations in similar objects. They point toward distinct formation mechanisms. Theoretical models now commonly invoke different source populations. Repeating bursts might come from young magnetars in active star-forming regions. One-time events could result from catastrophic mergers or collapses that destroy their sources. The two-species hypothesis explains why repeating and one-time fast radio bursts show such different statistical properties. If they truly arise from separate object classes, their distinct behaviors become natural consequences of different underlying physics. Could the two fast radio burst populations be related through evolutionary processes? Several scenarios connect repeating and one-time events through source evolution over astronomical time scales. One possibility suggests that repeating sources eventually exhaust their burst production capability. After producing hundreds or thousands of individual bursts, the source mechanism shuts down. The final burst in the sequence might be unusually powerful, resembling one-time events. An alternative scenario proposes the opposite evolution. Young sources might initially produce single, extremely powerful bursts that deplete most of their available energy. Surviving sources could then transition to a repeating phase with lower energy individual bursts. Both evolutionary models predict observable signatures that can be tested against fast radio burst statistics. The relative numbers of repeating versus one-time sources, their energy distributions, and host galaxy ages should reflect the evolutionary pathways connecting these populations. Dead stars can pack the strongest magnetic fields in the known universe. These cosmic magnets, called magnetars, might hold the key to understanding fast radio bursts. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. A magnetar's magnetic field could erase every credit card on the planet from the distance of the Moon. These dead stellar cores contain more mass than our entire Sun crushed into a sphere, just 20 kilometers wide. The magnetic fields in magnetars aren't stable. They crack and snap like breaking cables under enormous stress. When magnetic field lines suddenly rearrange themselves, they release energy equivalent to millions of nuclear bombs in milliseconds. This magnetic reconnection process creates exactly the kind of brief, powerful radio emission observed in fast radio bursts. The energy release happens fast enough and carries enough power to explain even the most extreme fast radio burst observations. Two neutron stars locked in a deadly spiral create one of the universe's most violent events. Their final collision might produce the most powerful one-time fast radio bursts ever observed. Binary neutron star systems gradually lose energy by radiating gravitational waves. These ripples in spacetime carry away orbital energy, causing the two dead stars to spiral closer together over millions of years. The final merger happens incredibly quickly. In the last few milliseconds before contact, the neutron stars reach incredible speeds and temperatures. The collision completely destroys both objects, creating either a black hole or a single, more massive neutron star. The extreme conditions during merger could generate coherent radio emission intense enough to create fast radio bursts visible across cosmic distances. This would explain why the most powerful fast radio bursts never repeat. Their sources literally no longer exist. Supermassive black holes lurk at the centers of galaxies, waiting to shred anything that ventures too close. A neutron star's fatal encounter with such a monster could produce spectacular fast radio bursts. Tidal disruption occurs when gravitational forces from a massive object overcome the internal forces holding a smaller object together. The black hole's gravity pulls more strongly on the near side of the neutron star than the far side. This differential pulling stretches the neutron star like taffy until it completely breaks apart. The disruption process releases enormous amounts of energy in a matter of milliseconds as the neutron star's matter streams toward the black hole. The intense magnetic fields and high-energy particles created during tidal disruption could generate the coherent radio emission characteristic of fast radio bursts. Each disruption event would be a one-time occurrence, explaining the non-repeating nature of the most powerful bursts. Cosmic strings represent some of the most exotic objects that might exist in our universe. These theoretical structures could be invisible highways of pure energy stretching across cosmic distances. According to some theories, cosmic strings formed during the very early universe when different regions of space underwent phase transitions at slightly different times. These transitions left behind one-dimensional defects in the fabric of spacetime itself. cosmic strings would be incredibly thin but enormously dense. A string thinner than a proton could contain the mass of an entire mountain range. When sections of cosmic string vibrate or reconnect with other strings, they release tremendous amounts of energy. The energy release from cosmic string events would happen very quickly and produce exactly the kind of brief, powerful radio emission seen in fast radio bursts. However, cosmic strings remain purely theoretical. No direct evidence for their existence has been found. Exploding stars create expanding shock waves that travel through space for thousands of years after the initial explosion. These shock waves might trigger fast radio bursts when they collide with particularly dense pockets of interstellar material. Supernova explosions blast material outward at speeds of thousands of kilometers per second. This creates a shock wave that compresses and heats any gas or dust it encounters during its journey through space. When the shock wave hits an especially dense cloud of interstellar material, the collision can accelerate particles to extremely high energies. Under the right conditions, these high-energy particles might produce coherent radio emission through collective plasma instabilities. The timing of such events would be unpredictable, depending on the random distribution of dense material in space. This could explain the apparently random arrival times and locations of fast radio bursts throughout the universe. Newly formed neutron stars are cosmic teenagers, young, energetic, and prone to violent outbursts. Their combination of rapid rotation and extreme magnetic fields creates conditions ripe for producing fast radio bursts. Young neutron stars can spin hundreds of times per second, while maintaining magnetic fields quadrillions of times stronger than Earth's. This combination creates a magnetosphere, a region of space dominated by the star's magnetic field. It extends far beyond the neutron star itself. The magnetosphere of a young neutron star is highly unstable. Magnetic field lines can become twisted and tangled by the star's rapid rotation. When these field lines suddenly snap and reconnect, they release enormous amounts of stored magnetic energy. These magnetospheric disruptions could accelerate particles to nearly the speed of light and generate the coherent radio emission observed in fast radio bursts. As neutron stars age and slow down, they become less prone to such violent outbursts. Not all neutron stars form from single massive star explosions. Some might result from the collision of two white dwarf stars, the dense remnants of Sun-like stars that have exhausted their nuclear fuel. White dwarf mergers occur when two of these stellar remnants spiral together and collide. If the combined mass exceeds a critical threshold, the merger produces a neutron star rather than a larger white dwarf or immediate explosion. The newly formed neutron star from a white dwarf merger would have unusual properties compared to neutron stars born from supernova explosions. It might have different magnetic field configurations, rotation rates, or surface compositions that affect its radio emission properties. The initial activity of such merger-born neutron stars could produce fast radio bursts with characteristics distinct from those generated by other mechanisms. This diversity might explain some of the observed variety in fast radio burst properties. Inside neutron stars, matter exists under conditions so extreme that the normal rules of physics might break down. Under sufficient pressure, neutron star matter could undergo a phase transition to an even more exotic state called quark matter. Quark stars would be composed of free quarks, the fundamental particles that normally remain confined inside protons and neutrons. This transition from neutron matter to quark matter would release enormous amounts of energy. The phase transition might not happen all at once. Instead, it could proceed in stages as different regions of the neutron star convert to quark matter. Each conversion event would release energy and potentially trigger fast radio burst emission. This model could explain both repeating and one-time fast radio bursts. Multiple phase transition events in the same neutron star would produce repeating bursts, while complete conversion might create a single, extremely powerful burst that ends the sequence. Black holes formed in the early universe might be exploding right now, releasing their final energy bursts as fast radio bursts. These primordial black holes would be much smaller than those formed from stellar collapse. Stephen Hawking showed that black holes slowly evaporate by emitting radiation. Smaller black holes evaporate faster than larger ones. A black hole with the mass of a mountain would take longer than the age of the universe to disappear completely. Primordial black holes formed shortly after the Big Bang would have had 13 billion years to evaporate. Those with the right initial mass would be reaching their final evaporation phase right now, releasing their remaining energy in dramatic bursts. The final moments of black hole evaporation would release energy across the entire electromagnetic spectrum, including intense radio emission. However, primordial black holes remain hypothetical. Their existence has never been confirmed through direct observation. Could fast radio bursts be artificial signals from advanced extraterrestrial civilizations? This possibility, while speculative, deserves scientific consideration given the unusual properties of these cosmic signals. Advanced civilizations might use powerful radio beams to propel spacecraft across interstellar distances. The concept, known as beam-powered propulsion, would require enormous radio transmitters capable of generating the energy levels observed in fast radio bursts. Alternatively, fast radio bursts might be leakage from alien communication systems or industrial processes. Any technology capable of manipulating the energy scales involved would represent a civilization far more advanced than humanity. However, the natural explanation remains more likely. The random timing, cosmic distances, and physical properties of fast radio bursts are consistent with astrophysical phenomena rather than engineered signals. The alien hypothesis serves mainly to remind scientists to consider all possibilities. Dark matter makes up most of the universe's mass, but remains completely invisible to telescopes. One theoretical dark matter candidate, called the action, might occasionally convert into detectable radio waves under extreme conditions. Actions are hypothetical particles that would interact very weakly with ordinary matter and electromagnetic fields. They could pervade the universe as dark matter while remaining essentially undetectable through normal means. In the presence of extremely strong magnetic fields, actions might convert directly into photons through a process predicted by quantum field theory. The radio emission from action conversion would appear as brief, powerful bursts. Magnetar environments provide exactly the strong magnetic fields needed for efficient action to photon conversion. If action dark matter exists and accumulates around magnetars, periodic conversion events could produce the fast radio bursts we observe. The most exotic emission mechanism proposed for fast radio bursts involves the amplification of radio waves through relativistic plasma processes. This synchrotron maser mechanism could produce the extreme brightness and coherent emission observed in fast radio bursts. Normal synchrotron emission occurs when charged particles spiral around magnetic field lines, producing radio waves. In most cosmic environments, this creates a smooth background of radio emission without any special organization or amplification. Under extreme conditions involving ultra-relativistic particles and precisely organized magnetic fields, synchrotron emission can become coherent and amplified like laser light. This maser effect can increase radio brightness by factors of millions or billions. The challenge lies in creating the perfect conditions needed for synchrotron maser operation. The mechanism requires precisely aligned magnetic fields, particle distributions, and plasma densities that might exist only in the most extreme cosmic environments like neutron star magnetospheres or relativistic shock waves. Time itself might control when some fast radio bursts decide to fire. FRB 180916 shattered assumptions about random cosmic explosions by following a precise schedule that repeats every 16 days. This remarkable source was discovered by the Shiramu telescope in Canada. Unlike other repeating fast radio bursts that seem to fire randomly, FRB 180916 showed clear evidence of predictable behavior. For 4 days, it produces multiple bursts. Then it goes completely silent for 12 days before resuming activity. The 16-day cycle repeats with clockwork precision. Scientists can now predict when FRB 180916 will be active and schedule observations accordingly. This predictability represents a completely new category of fast radio burst behavior. The regular timing suggests that something in the source environment operates on 16-day timescales. Possible explanations include orbital motion around a companion star or periodic changes in the magnetic field environment surrounding the neutron star source. Scientists finally caught a fast radio burst in the act within our own cosmic neighborhood. On April 28, 2020, a known magnetar in our galaxy fired a radio burst that looked remarkably similar to the mysterious signals from distant galaxies. SGR 1935 plus 2154 is a magnetar located about 30,000 light-years away in our Milky Way galaxy. Astronomers had been monitoring this supermagnetic neutron star for years as it produced X-ray flares and gamma-ray outbursts. The radio burst from SGR 1935 plus 2154 was much weaker than typical fast radio bursts from other galaxies, but it showed the same characteristic frequency sweep and brief duration. For the first time, scientists had a confirmed fast radio burst source they could study in detail. This galactic fast radio burst proved that magnetars can indeed produce fast radio burst-like emission. However, the event was hundreds of times weaker than extragalactic fast radio bursts, suggesting that different mechanisms or extreme conditions are needed for the most powerful bursts. Traditional radio telescopes hunt for fast radio bursts one small patch of sky at a time. The Canadian Hydrogen Intensity Mapping Experiment changed this approach by monitoring huge portions of the sky simultaneously every single day. Xiamen doesn't look like a typical radio telescope. Instead of a large dish, it consists of 4 long cylindrical reflectors that can observe large sections of the northern sky continuously. This unusual design makes it perfect for fast radio burst discovery. The telescope's wide field of view allows it to detect fast radio bursts at an unprecedented rate. Xiamen finds dozens of new fast radio bursts every month, multiplying the known population by factors of 10 in just a few years of operation. This detection revolution transformed fast radio burst research from studying individual rare events to analyzing large statistical populations. Scientists can now investigate patterns, correlations, and systematic properties that were impossible to study with small sample sizes. Not all galaxies create the same types of fast radio bursts. FRB 190523 provided crucial evidence that galaxy type determines whether fast radio bursts repeat or occur just once. This particular fast radio burst originated from an elliptical galaxy filled primarily with old, red stars. Elliptical galaxies have largely finished forming new stars and contain relatively little ongoing stellar activity compared to spiral galaxies like our Milky Way. FRB 190523 fired once and never repeated despite extensive follow-up observations. This behavior contrasts sharply with repeating fast radio bursts like FRB 121102, which come from younger galaxies actively forming new stars. The correlation between galaxy type and fast radio burst behavior provides strong evidence that different stellar populations create different types of sources. Old stellar environments apparently favor catastrophic one-time events, while young star-forming regions produce sources capable of multiple outbursts. Some repeating fast radio bursts have cosmic companions that never stop broadcasting. These persistent radio sources represent a new puzzle in the fast radio burst mystery. Persistent radio sources appear as steady, weak radio emission that continues between fast radio burst episodes. Unlike the brief millisecond flashes, these sources emit radio waves continuously for months or years. The persistent emission comes from the exact same location as the fast radio bursts, suggesting they share a common origin. However, the persistent sources are thousands of times fainter than individual fast radio bursts and show completely different spectral properties. Only some repeating fast radio burst locations show persistent radio sources. This suggests that different repeating sources operate under different environmental conditions, with persistent emission indicating particularly active or energetic source environments. The future of fast radio burst research will be revolutionized by the Square Kilometer Array, the most ambitious radio telescope project ever attempted. This facility will detect thousands of fast radio bursts daily across both hemispheres. The SKA will consist of thousands of individual radio antennas spread across sites in Australia and South Africa. The combined collecting area will equal 1 square kilometer of radio gathering surface, making it 50 times more sensitive than current facilities. This unprecedented sensitivity will enable detection of even the weakest fast radio bursts from the most distant galaxies. Scientists will be able to trace fast radio burst evolution across cosmic time and map their distribution throughout the observable universe. The SKA's capabilities will transform fast radio burst research from a discovery-driven field into a precision science. With thousands of detections daily, astronomers will finally have the statistical power to definitively test theoretical models and understand the physics of these extreme cosmic phenomena. Fast radio bursts have evolved beyond astronomical curiosities into powerful tools for studying the universe's most mysterious components. Their signals probe both dark matter and dark energy across cosmic distances. Dark matter interactions with fast radio burst signals could leave subtle signatures in their arrival times or frequency spectra. Even tiny delays or distortions could reveal the distribution and properties of this invisible cosmic component. Dark energy affects the universe's expansion rate, which influences how fast radio burst dispersion measures relate to distance. Precise measurements of this relationship using thousands of fast radio bursts could constrain dark energy properties better than current methods. The combination of fast radio burst distance measurements with other cosmological probes will provide independent tests of our understanding of cosmic evolution. These radio signals offer a completely different perspective on the universe's composition and fate. Future fast radio burst discoveries will coordinate with gravitational wave detectors and space telescopes to create complete pictures of cosmic catastrophes. This multi-messenger approach reveals physics invisible to any single type of observation. When neutron stars merge or black holes form, they might produce gravitational waves, gamma-ray bursts, and fast radio bursts simultaneously. Detecting all three signals from the same event would provide unprecedented insights into extreme physics. The coordination requires split-second timing across multiple observatories worldwide. Fast radio burst detections must trigger immediate alerts to gravitational wave facilities and gamma-ray satellites within minutes of the initial radio detection. Multi-messenger observations of fast radio burst sources will finally resolve debates about their physical origins. The combination of radio timing, gravitational wave signatures, and gamma-ray spectra will uniquely identify the mechanisms creating these mysterious signals. Could some fast radio bursts be artificial signals from advanced civilizations? The search for extraterrestrial intelligence, or CTI, now includes fast radio burst research in its quest to find technological signatures. Advanced civilizations might use powerful radio beams for interstellar communication or spacecraft propulsion. These engineered signals could be misidentified as natural astrophysical phenomena if we don't look carefully for artificial patterns. CTI researchers analyze fast radio burst timing, frequency structure, and polarization properties for signs of intentional design. Natural astrophysical processes rarely create the precise mathematical relationships that technological signals would display. While most fast radio bursts likely have natural explanations, the search for artificial signatures remains scientifically valuable. Even negative results help constrain the prevalence and signaling methods of hypothetical galactic civilizations. Dozens of different theories attempt to explain fast radio bursts, but no single model accounts for all observed properties. The field desperately needs a unified theoretical framework that connects the various pieces. Different fast radio burst types might require different source mechanisms. Repeating low-energy bursts could come from magnetar flares, while one-time high-energy events might result from neutron star mergers or black hole formation. A comprehensive framework must explain not just the radio emission mechanism, but also the correlations with host galaxy types, the energy distributions, the activity patterns, and the rate evolution across cosmic time. Theoretical progress requires close coordination between modelers and observers. Each new discovery provides additional constraints that theoretical models must accommodate, gradually narrowing the range of viable explanations for these cosmic mysteries.